inverse of the exponential functions are logarithms, and logarithm functions are slow, still increasing, but slow, versus exponential functions are very fast. Logarithm functions are used in science to slow down processes. You will see someday, maybe at the conference, someone presenting something and shows x-axis and y-axis. And instead of x and y, it will be ln x and ln y, or maybe ln of time, and so on. And they have to mention this. They will say, just for you to know, the Cartesian coordinates here used logs to slow down the process, because original process was so fast, like a nuclear explosion. It was like this, and you're like, okay, how can I work with this fast process? To slow it down, we apply logs for all cases, and then you see how it's actually bounce, and then goes up. And now you can see maximum, minimum, what timing it took, and so on. So logarithms actually are very useful. They are everywhere in scientific articles, publications. You will see them quite often. Last time I mentioned, to find inverse function, you build y equals x and use it as a mirror. You're reflecting your function with respect to that y equals x function, like a mirror. So exponential function y equals a to the x looks like this. The pink one goes through 0, 1, because when you plug 0, you get 1. Versus logarithm y equals log base a, this is how you should see it, only works for positive a. You see how we've reversed it, reflected with respect to y equals x. Now, since it's reflected, it goes to the point 1, 0 instead of 0, 1, and so on. Where exponential function was going up really fast, logarithm is going up really slow. Where exponential function was going to 0 on the height level, logarithm goes to negative infinity. And we have to discover all of those ideas right now and to remember the formula. The most important idea here is how to jump between logarithm and exponential function. If you're given an exponential function x equals a to the y, then logarithm will be y equals log base ax. That's how they are undoing each other. Think about this. Y equals log a of x. Inverse function asks you, I know y, but I want to find x. How to find x? How to undo logarithm? You apply exponential function, and x now is found. It's isolated. X equals a to the y. Kind of hard to memorize though. And this is how I did it. You see this a over here? A is in the base. A should stay in the base. That is how I remembered it. Y used to be isolated. Now it's not going to be anymore. That's the whole purpose, to flip what's the meaning of y and x. Y used to be output. Now y will be input. X used to be input. Now x will be isolated output. Make sense? It will take you some time to remember that, but not too bad. Okay, I'm not going to be deleting all of this. Okay. I will just remember base and the base. Base stays the base. A. Positive. Here's some explanation. Do you guys have questions? No? You're fine. A is the base. A should be positive, not 1. Y should not be 0, and so on. For example, log base 2 of 8 equals, you basically ask yourself, 2 to what exponent gave me 8? That's exactly what's the idea of logarithm function. Look at this. Ask yourself in your mind, 2 to raised to what gave me 8? And you're like, 2 times 2 times 2 is 8. So 2 to the 3 is 8. That's exactly the idea of this, going to the left and going to the right. 2 was the base, stays the base. Result becomes my input. Input becomes my answer. Make sense? That's the idea. And vice versa. So 2 to what gave me 8? That's logarithm. 2 to log base 2 of 8 is 3. So 2 to the 3 gave me 8. That's the idea. Questions on the bed? I will go fast in these topics because we kind of hope you know this from pre-calculus class. But if not, check all the notes. You'll feel comfortable with this pretty fast. Based on the graph, let's figure out domain and range. Who remembers what's the interesting idea about the domain and the range? Domain and the range for the inverse functions. So y equals a to the x. That's a pink one. If you're colorblind, let me know, but that's the one on the left. Going up. What is the domain for exponential function? Domain is all the positive inputs. Whatever we are allowed to plug into the x. Or just even from the graph. Where are all my inputs? What do you think? Negative infinity, positive infinity. Do you all agree? Just because I have approving voice, it doesn't mean it's correct. So just to make sure. You all agree? Yes. Okay, good. I should fix my approving voice. But yes, it makes sense to say that all inputs are fine for a to the x. A to the pi, it's number. A to the negative 0.7, it's number. Whatever. Anything is fine. So minus infinity, plus infinity. The range is where my outputs are located. For a to the x, what are my outputs? What do you think? Do you all agree with this or not? Now I don't have approving voice anymore. So like, also including 0 or not? So how do you know? How do I know? How do we all know? We're looking like this. Where are my outputs? My outputs for the pink function, a to the x, seems to be always above x-axis, right? Then it means negative numbers cannot be the answer because a to the x cannot give you negative. How do you imagine? 2 to the 7 cannot be negative. 2 to negative pi cannot be negative, and so on. But also, can it be 0 or not? Will it ever touch the x-axis? No. No matter what you plug into the x, the smallest number will be still not 0. It can be 0.00007 or 1, but it will not be 0. So the range is 0, not including it, to infinity. That's the idea. Then, what do you remember? Now let's do the same thing with the log. What do you remember from the previous class about domain and range for the inverse functions? What was some interesting feature about these two? What do you remember? They swap places, exactly. That's a very good answer. It's exactly what I showed you last time. Since input and output exchange between each other, then whatever used to be possible input becomes possible output. Whatever used to be possible output becomes possible input. So, technically speaking, I don't have to look at the graph. I just say this will be my domain from the range, and then this will be my range from a domain. But let's check. What is the possible input for the logarithmic function? Do you see we cannot plug negative numbers? It's the green function always is on the right, from y-axis. And we also cannot plug 0. So it means the domain now will be from 0 to plus infinity, which is exactly the range for the previous function. Now, what about the range? Seems like it can be negative, and it can be anything positive. It grows, just very slow, but it keeps growing forever. So at some point it will be log at infinity is still infinity. Just it will take it a while to get there. So outputs are negative infinity and plus infinity. Do you all agree on this? And that's science over here. We're doing science here. We're actually building a new function and making conclusions about where this function lives. What does it do? Where the inputs are and where the outputs are based on the inverse we knew before. Actually, there's a debate which one came first, exponential function or log. And in different books, they're teaching exponential function, logarithmic function coming from integration. And in different books, they're showing first exponential functions coming from the limit. So that's pretty interesting that they're still debating on this. Before finishing the last box, I gave you these two graphs separately. For you to know, especially we're going to be testing this, and it will be part of the limits. We're jumping back to the limits idea. The first one is exponential, a to the x. A to the x. This x is too big over here. What is the limit of this function a to the x when x goes to plus infinity? X goes to plus infinity, it's over here. So I'm asking about the output. What do you think is the first limit? Go up, right? So forever. Plus infinity. And we knew that. I told you before. Exponential function is infinity. And it goes there very fast. Faster than log, faster than polynomial functions, faster than, I don't know, square root of functions, and so on. So it's fast. The faster one only, which one do you remember? Factorial. Factorial was faster, but we don't really work with factorials in calculus 1 class. We will work with them in calculus 2 class. What happens with exponential function when x goes to minus infinity? That's this way. Approaches 0. Do you all agree with this? Do you see this thing? It approaches 0. It will get super close to 0. But do you think it will ever reach it? No, seems like it will never reach it. What does this indicate to you? Asymptote. Good job. Do you all see it? It approaches somewhere super close but will never reach it. Also, when x goes to a very big negative number, that's how we like saying it, big but negative numbers, the answer is a number that indicates an asymptote. Which kind of asymptote? Horizontal or vertical? Horizontal asymptote. Go here to the exponential function first row. Asymptote is, there's a horizontal asymptote, y equals 0. All agree? So interesting that it only matters on the left. On the left, it's approaching it and never gonna reach it. On the right, it doesn't care about asymptote. It just goes up forever, very fast. Let's see what's happening with log. It's an inverse function. It should be something like that, but a little bit different. What happens in the long run? In the long run, let me be consistent, put plus here. Same idea. In the long run, what happens with log when x becomes super far to the right, which means super big numbers and positive? F of x goes where? Infinity. You might think there's some kind of asymptote. Not really. It's keep growing like this, like just slow, but it's going up, my point. So it's still plus infinity. Remember, at infinity is exponential functions, logs, they go to plus infinity. They keep growing, just different speeds. How about negative infinity? Can I even set x go to negative infinity? If I say x go to negative infinity, that means I'm saying x goes to a very big negative numbers. But we just pointed out over here in a domain. What does this mean? Yes, it approaches 0, but I want to say that we cannot plug negative numbers. Make sense? So at some point we have to stop plugging small numbers. Where do we stop? We stop around 0. So we're approaching 0. Also, we're approaching 0 not from both sides. If you remember what it means, I'm approaching 0 from the right side limits. That's like chapter 1. What happens when I'm approaching 0 from the right? What happens with log? What do you think? Who is waking up only now? It's a little bit too late. Where do I look? What did you say? Where do I go? Negative infinity. Good job. I'm going down forever. So on the right, I'm going up, but slowly. And on the left, I'm going down and fast. That makes sense. Look at exponential function. On the right, I'm going up and fast. On the left, I'm decreasing to 0. Log is inverse. On the right, I'm going up, but slow. On the left, I'm going to 0. I'm going to down to negative infinity, but fast. So it's reversing. It's reversing the whole idea of it. Well, does this remind you anything? X approaches a normal number. Y approaches an infinity. Basically blows up, even though it's in a negative blow up, to negative numbers. What does this indicate? An asymptote. Which one? Vertical. Good job. So go up. Yes, what did you say? X is? So the asymptote is like the asymptote output tells you plus infinity, minus infinity. But location should be a number. Number comes from here. So we say x equals 0, y goes down forever. Yeah, good job. So this is basically what rules you will have to use. And you will see how we're going to be using it for the limits. And we're going to have more limits again. Don't freak out. But it will be pretty interesting with all of these guys. Now, since those two... Okay, questions. What do you guys think? Not too bad. I'll put...
Technically the inverse, f negative 1, is really literally the inverse?
Yes, it is. Actually, I will show you right now. Good question. It is inverse. It looks like this. Log AX is basically inverse of x for f of x to be a to the x. It's literally inverse, but it's so common. It's so common, and especially found in the nature all the time, that we decided to give it the name natural log. It was when the first mathematician discovered log, and actually he was literally making a tables, log of 0001, log of 0002, and then it was like a time with no calculators and internet. He was literally having a hobby out of it, like calculating each number. There's a table how he discovered all of this, and then he just was so obsessed about this. The name show up, log. Then we notice that nature using logs all the time, and we call it natural log. Very interesting. You will see it everywhere. You will see it everywhere. Trees are growing using natural logs. Some trees on the edge of the canyon in Yellowstone and different canyons, did you notice they do spirals like this at the trunk? They have their spirals. Notice next time when you see. That's using a naturalist idea of exponential natural logs. They spiraling to avoid wind, because when wind approaches, some aerodynamics happens and it goes around it instead of pushing it down and breaking it. So nature literally using mathematics to adapt to the situation and survive, and so on. So it's very interesting. Log is literally everywhere. Inverse functions. To show you again idea of inverse function, what do you think gonna happen if I am going to apply log of the base a to the exponential function a to the x equals? Then what is going to happen, since I just mentioned, and it was a good question, that log is literally an inverse for the exponential function. Let's see, let me write down. Inverse for exp. So log is inverse for the exponential function. Then if I'm applying log to the exponential function, what should happen? What did you say? What do you guys see? It gives you back the input. What was the input? X. X will be the answer. Like we did in the last class. In last class we had the same situation. F minus applied to f of x gives you x. F applied to f minus of x gives you x. Log an exponential function undoing what happened. So the result will be the input x. What happens if I'm using exponential function and applying it to the log in the exponent? What do you think now? Log ax. How about now? Here's my input. Think about this. Log of x, and then exponential function undoing what log does. So the answer is yes, x again. The only requirement is that this base should be the same. That's the only way it works. If you have like one base is 5 and the other one is 7, it doesn't work anymore. It's a little bit shifted. But if it's the same, that's what you do. And that's what we're going to be using quite a lot, because sometimes we don't like logs. So we're applying exponential function with the same base to get rid of the log. Sometimes we don't like exponential functions. They're too fast. We're applying log to slow it down, work with logs, and then going back to exponential functions. Put this into the box. That's basically the main idea of inverse functions. So they are inverse of each other. Inverse of each other. That's the idea. Make sense? More stuff. Before we even go to differentiation, basically the whole point of this lecture is to introduce exponential and logarithmic functions and teach you how to differentiate this. In the future, we're going to learn how to integrate this. But to get there, I still need to review tons of stuff about logs. Laws, or basically properties, but laws of logs. And those are very interesting. Logs have very unique properties which are very useful in engineering and science in general. I just told you several times that log slows down the process, and that's very convenient. If something goes too fast, you just apply log and it works. It works fine. It slows down everything, and you can work with the process like in slow motion. Work with it fine, concave up, concave down gradient, where is the fastest point, and so on. So interesting to point out that log of the product x times y makes it slower by breaking it down to the addition of two logs, log of x plus log of y. But the base should be the same. You see how it slows down everything? Product rule is too fast, a product is too fast, so we're making sum out of that. If you're a computer scientist, you should know that basically 10 years ago, memory was quite important, and whatever you're coding was supposed to match some kind of memory limit of the device. Logs were used into this as well because we can calculate the speed of the product. It takes a lot of memory to calculate the product for the computer, and it takes much less memory to calculate the sum. So we were using this quite a lot to speed up the process. Then guess what happens with the quotient? X over y. What do you think is gonna happen? The quotient. Probably minus, right? So that makes sense. If you have a quotient and you don't like it, you can actually transform it into the difference if you're using logs. So a quotient gives you difference, very interesting. And now the most famous one, those top three are famous. The most famous one is this one. So again, you're coding. Your program tells you, I don't have enough memory to work with products. That's too much. You're applying logs. It gives you sums. It can do that. Quotients, the same thing. It gives you difference. But the most expensive step in computer science is exponential function. If you have log base a, and then you have x to the m. So let's, this is a polynomial. I'm not saying about exponential function, a polynomial. So here you have an input raised to some power. What is x to the m? That's x times x times x times x times x. If product is expensive, you can imagine having x to the m, it's even more expensive. It takes time to calculate. It gives a big error if it's too many numbers, digitals, and so on. After, how many digits do you need and how much to approximate. So what the log does, it's a very, very unique property, only log does it. It takes this exponent and put it down as a product. And that's a very big deal. What it becomes is m is standing outside now. M is standing outside times log base ax. And this one I would say probably is one of the most important. Well, I would say three are the top three most important because they slow down the process. You see? The computer doesn't like polynomials, x to the m, hard to calculate. Okay, apply log, m jumps down. And vice versa. If you don't like having a product and for some reason you want to have a polynomial, bring it up by using log. Very interesting. So m log ax will be log ax to the m. So that's a big difference. You can see when you get into higher level of computer science classes, especially if you actually explain how Java works, C++ works, how all those processes were created, they will tell you that actually makes a big difference. When it comes to the error, how big the error of each calculation, the error of this will not be the same as the error of this, because here I perform product only once, versus here I'm performing product m times. What if m is 1,000,000? There's a 1 point to multiply by the million ones versus x times x times x times x times x million times when x is 0.00017. That gives you a big error of calculations. And those three should be part of your memory from now on. Practice them, learn them, be good at them. More. For you to know, since there's one type of logs that was very common in the nature, we made it a different name. Log with the base e. So e, 2.7 blah blah blah, very well-known number, found in nature everywhere. You can see recursion in the nature. Even cauliflower has exponential e in there and so on. Anyway, since e is so popular, log of base e was agreed to rename natural log of x, lnx. And that's the one you probably saw many times. That's what we call natural log. Because it's literally everywhere in the nature. And that's the one we'll be working with mostly. Of course, I'm introducing the general case, log base 7 and so on, but actually usually we do logs, natural logs, ln x. Then one more was pretty popular, which is a log with the base 10. Appears to be popular. In your calculator, you will see those two. Then, since it's just too annoying to keep writing 10 all the time, we just quit writing it. And basically, if you see log with no base indicated, we assume that's base 10. So your calculator has those two only, natural log and base 10. No other bases over there. If we give you a different base, let me make a title, 6. Change of base formula. Change of base. What if on your exam I give you log with the base a and you don't have it in your calculator? So I will do log of the base a of b. And you have only log base 10 and log base e. How can you calculate it then? Well, there's a change of base formula which says whoever was on the top, b seems to be higher than a, goes to the top. So it's going to be b. Whoever was at the bottom, e was lower, a was lower. So it's going to be log a. What is the new base? Anything you want can be there. So I will call it c and c. Anything you want can be there. So you can create any new base you want and it works. And of course, since your calculators have natural log and log 10, we usually like doing ln b over ln a or log b log a. Again, how to remember, b was higher so it goes to the top, a was lower so it goes to the bottom. That's just a mnemonic way to memorize the formula. Change of base formula. And not yet done. Let's keep going with this. If I just introduced to you natural log and log base 10, definition, new definition. Y equals natural log of x, and I want to undo that, which means I want to find x. I want to find the input with the given output. How to do it? You're applying e to the both sides. This is how you should see. Of course, actually, there is a definition here, but also you can explain it this way. You're applying e to the both sides. E to the y equals, what is e to the log of x? If e undoes log, just x. And this is a definition. This is how you do it. That's a new definition using the most known logs. I would put it even in more colors just for you to know. This is like the most important thing actually you're supposed to know. And this is what we call definition. How to jump between these guys. If you given e to the y equals x, apply ln for both sides. You will get ln undoes e gives you y equals ln x. And that's exactly on the left-hand side, y equals ln x. This is how you should see the situation. Because, let me write down, because inverse functions undo each other. So ln of e to the x is x. E to the ln x is x. They just keep undoing each other and the result will be your input. What is the input? X is the input. Finally, a couple examples. Questions? Let me stop for a second. Questions? Yes?
Why is it number 6? Why is it log base c?
Oh, C, just any third one. So I did ABC. So I give you log. The question is why there's a C here. The base was A. The input was B. And say I don't like the base. It's the input whatever. But I don't like the A because my calculator doesn't have A. It has 10 and E. And then I can literally create any other different one. Of course, usually we do E over here. But just to be general for the formula case, I'm telling you literally anything you want. You can put C. With a new base, you get a quotient. Make sense? That's a good question, yeah. Just we recommend you to do natural log or the naked guy. Naked log is log base 10, log base A. Same thing, because your calculator has that. But natural log is the most popular. More questions? What do you think? Might feel like I go too fast. We just kind of hope you know some of these things. But if not, you see, it's not too bad. Like, it's not too bad. Question number 1. What do you think is going to happen if I have ln E? What is that? Very interesting question. Based on the definition, check the definition. So what is ln E? ln is log base E, right? And now E matches with E. Who said 1? How do you know? It is 1, but how do you know? Yeah, exactly. Basically, you should ask yourself, you see the definition? Or like even understanding, you ask yourself like this. E to the what gave you E? How do I know it's the same thing? Because I'm giving you here log base E of E, right? Question mark. So to undo the question mark, you use definition or common sense of the question. E to the what gave you E? E to the 1 gave you E. So that's how you know that the answer is 1. Make sense? I will keep question mark like this. And then I will say ln E is 1. We will have this quite a lot, actually. ln E happens in many calculations. You will see it later. Now, how about these guys? 2. How about ln 1 over E squared? That's not very obvious. So I will go with you on this step by step. Let's see. ln of a quotient. ln of the quotient. 2 ways to see it. Either we're breaking down in a difference, we can do that, or we see it as exponential function inside. So way 1. Let's do question mark. Way 1. I just told you that log undoes quotients, right? So a quotient will give me a difference. 1 minus the top minus the bottom. Put parentheses like this. Make sense? That's what one of the properties says. Property number 2. Property number 2 says if you have a quotient breaking down to difference, it slows down the process and it's nice. What is ln of 1? What do you think? Let me add it here into 1. Let's do 1 prime. What is ln of 1? 0. How do you know? You're kind of asking like, so base is E to the question mark, right? Exactly, equals 1. E to what power gave me 1? E to the 0 gave me 1. So remember that. 1 prime. Not prime, like let's just do whatever. 1 star. 1 star. So remember these as well. This first one is 0. Then what to do with ln E squared? 2. Something should be done with a 2. What should we do with 2? Yes, property number 3. Let's put it down. Take it and put it down. It's upstairs over there. Not convenient. Put it down. Because products are easier to work with than exponents. So what we're going to have will be 0 minus 2 ln E. What is that? What is ln E? 1, right? So the answer will be negative 2. Or way 2. Way 2. How about I see it not as a fraction? How about I see it as ln of E to the negative 2 right away? Because ln of 1 over E to the E squared is E to the negative 2. How about that? Then I can just do the last property right away. Take this exponent and put it down. Negative 2 times ln E. ln E is what? 1. So the answer is negative 2. This way is faster. Make sense? Did you get lost? It's fine if you do a little bit. Logs are a bit confusing at the beginning, but I should tell you it's not too bad. Logs, you get used to those awkward properties and then you're good at it. At some point you're good at it. How about this one? Example number 3. Example number 3. It keeps getting harder. I'm on purposely increasing the intensity of the situation. You will see the third example will be crazy. But for now, this. Can we do this one? This should be a very nice number. Very nice number. I can even tell you it's 49. How come this is 49? No way. Like how? E to the 2 log 7. 49. Really? Like how is it even possible? What do you think we should do? I told you that E undoes log, but this 2 is like on the way. You cannot undo E with 2 times log. Okay, so that's not good. What do you think? Yes?
Did you do the reverse of the property we did in 22?
Third one. Exactly. Yes. Let's reverse the property and put it up. Let's jump it up to the exponent, right? Before that, we put it down. Now, let's pop it up over there. It's going to be E ln 7 squared, right? Now, what do you see? E to the ln. Even when you say it out loud, it should sound weird. E to the ln, that's the input. E undoes ln. ln undoes E. What is the input, though? Put these guys in parentheses. This is your input. 7 squared is your input. So the answer is 7 squared, which is 49. Make sense? And now the crazy one. Can you do the crazy one? And this is what we kind of want you to know. Like it's supposed to get to this level, which has a huge fraction. Then a product, x to the 4 times then a square root. Of course, why not? X minus 1, and then everything all over a polynomial, 3x minus 4. And you might be surprised, but this is exactly what you might be doing for your career at some point, which is working with complicated functions, applying log onto products and quotients to make them simpler. That's a very interesting idea here. We're going to apply logs, and the result will be better. Because I will ask you to differentiate this, basically, in a second. I don't want to differentiate that. Look at this fraction. It has product rule, it has quotient rule, and it has chain rule. Can we get rid of all of this? Yes, if you use logs. If you use logs, you will not be needed to use quotient rule and product rule. Maybe even chain rule will go away. And that's why logs is like this magical function that helps us to make hard situations simpler, work with logs, work, then go back using exponential function to the original thing. Let's do it. We're going to be using all our properties carefully here. First, the thing I see is a huge fraction. I don't like fractions. Not personally, but like in this situation, I see a fraction. I don't like this fraction. Let's get rid of it. Log is the one that helps you to get rid of the fraction. Log says takes the top minus the bottom, right? That's the property number 2. I can even name it property number 2 if you want. So it becomes natural log of the top numerator, x to the 4 times x minus 1, put parentheses, minus log of the bottom, natural log of 3x minus 4. Do you all agree? So, boom, fraction disappeared. This looks better. I don't have a fraction. That's nice. Fraction has this division by 0 thing. Asymptote shows up sometimes, or some kind of denominator problem. You see, now we don't have it. That's good. That's why we like it. Now I see a product. X to the 4 times the square root. Let's break this one down. Log says if you have a product inside, then it will be log plus log. So it will be property number 1. Log of x to the 4 plus log of, can I write down a square root as 1/2 if you don't mind? Like this? Thank you. Minus log of 3x minus 4. And now, almost done. What is this over here? Okay. Now, let's work with exponents. X to the 4 is annoying. The square root, which is now 1/2, is annoying. Let's get rid of these guys. And that's property number 3. Let's put this 4 down. Let's put this 1/2 down. Then it becomes 4, the natural log of x to 1. You see? 4 goes down to 1. Plus 1/2 natural log x minus 1 minus natural log of 3x minus 4. And this is the answer. I actually never wrote down what I wanted from you to do, but the question usually sounds like rewrite the given log with the difference of sums of logs with this most simplified version. I think that's how this sounds usually. I'm gonna put it in the quiz next week, and that's what usually we say. How do we know that we stopped? You see, I never touched this guy. Stop here and stop here, because there's no formula for the log of difference and log of sum. Remember, it takes product, quotient, and exponents and make them slower. It creates sum, difference, and the power goes down. Not the other way around. It doesn't work with differences and sums. So don't touch that. X minus 1 through x minus 4 doesn't do anything here. So just to make sure you understand this, note ln of x plus or minus y, there's no formula for that. We don't really do anything with that, because it's already slow enough. Why you want to bother that? Questions? What do you think about this? Not too bad. I think it's not too bad. Usually students getting it pretty good. Derivatives, logs, and its properties. Let's see what this problem is. Yes. Can you figure out this problem in Socratic